coded things I had to get through to the European Union to see you guys, lots of fake documents created, and I'm happy to be here. So, I am Konstantin Klado, I am a CTO of Skale. Skale is a network of Ethereum-compatible blockchains, which does all kinds of interesting things. In particular, we can host websites, do all kinds of really fast transactions, and it's all Ethereum-based and Ethereum-native. So you can use Skale for many interesting projects. Now, I'm going to talk today about something, because I'm actually also, in my former life, I'm a researcher. I've been doing mathematics for quite a long time. And then I was also working for the US government for cryptography analysis for different products. So I'm going to tell you guys a little bit about a really interesting mathematical object, which is called threshold encryption, threshold signatures. And it actually turns out to be really useful. Before I start, I just want to ask several questions. The first question is, how many of you guys have an engineering, like undergraduate degree, computer science or electric engineering? Okay, so now I think I understand the audience. So, how many of you guys heard about front running? Okay. How many of you heard about MEV, the strange acronym MEV, which is pretty much the same? So yes, let me just first probably then explain to you really in a really easy way what front running is. Front running basically means that someone, a really bad guys, and some bad guys actually find out about you doing something and they exploit and they actually make money. One example in the real life I can tell you about is I've been doing all kinds of startups, and one of my previous startups we actually filed in California, we filed for corporation, and then I was filing these papers for incorporation. Next day we have this email from God knows where, and the guy is saying, oh, actually I just registered the website which has exactly the same name as your company, and I'm going to charge you $1,000 for this website. So the guy actually found out that our corporation was being registered just on the California website, and the guy was actually exploiting it. This information, he registered the domain, and then he actually sold it to us. We paid him $1,000. Please raise your hand if you understood this thing. It's bad. And another example would be that if some musician like Rammstein, comes to Paris and I like Rammstein and I'm trying to buy a ticket, some bad guy finds out about it, buys this ticket and sells the ticket to me. Like if you go to music venues, in many cases you see these guys, the bad guys trying to sell you the ticket, and the ticket usually twice expensive. So that's pretty much the idea of front running. And actually, the same MEV is the same. It's called minor value extraction. But basically, that's when miners actually use front running to actually exploit additional value on the blockchain. So someone submits transactions on the blockchain, and the guys are actually exploiting this. So it's also very widespread on Wall Street. It's a very simple idea. Turns out that you can totally eliminate front running and totally eliminate MEV using an interesting mathematical object which is called threshold encryption. And I'm going to talk about this object for a little bit and how we use it at Skale. Now, in France, before the war, and also not only in France, in some other countries in Europe, people were doing mathematics. I think mathematics originally was just a way for rich guys to not be bored, because there was no things, there was no Game of Thrones, there was no internet, people literally couldn't do anything, and they were rich. And mathematics was a great thing to have fun, because the only thing you need to have is paper and pencil, and here probably, as Stalin said, we are in a historic building, and many of these guys are probably doing it here. So there was this person, his name was André Weil. He was a Jewish French guy, and he was a mathematician, and then the war started. He didn't want to go to the war, so he avoided drafting in different ways, and then they caught him, and they put him in jail. I don't know if the jail was here in Paris or somewhere else in France, but the fact is that he was actually in jail and then he had absolutely nothing to do. And so in jail he had paper, and he came up with this absolutely useless mathematical object, which is called while pairing, and it's a very obscure thing, which is called group theory. And in the group theory there are all kinds of crazy things, and one of them is while pairing. Is if you actually take two groups, and then like you actually glue them together, and you have some other strange object. And it was totally useless. And the guy actually got out of the jail, so actually he got to the army, and actually he went after from the jail, they put him into the army, so it was like the worst thing. But then it was this while pairing, and it turns out that as always in mathematics for a long time it was like totally useless. But then in 2001 approximately, people at Stanford, then Bonnet, Lin, and I believe Shahov, the other guy, they came up with an idea of a threshold signature, which was using this object while pairing, and since that while pairing is a hot subject of research and everything. Do you guys, please raise your hand if you don't know what a digital signature is? Okay, I'm going to explain to everyone, and it's going to be the best thing for you, because you'll know what it is. Even if you don't know, after this talk you'll know. It's a super simple thing. You have your secret key, right? And the secret key means that you only have it. Now, you can use computer to, you enter the key, and any document you can take, any statement, you actually entering the key, and it will generate like a small file, a mathematical object, and the mathematical object will prove that you signed the document. And the reason it's a proof is because only you actually have the key. You know, other people don't have the key, so if someone generated signature, the signature requires the key, it's your key, then you're screwed. If the government comes later and you sign this digitally, and the same as signing it using just a regular pencil. So that's the idea of a regular signature. And then there is an idea of threshold signature and aggregated signature. Please raise your hand, any of you which heard about threshold signature or aggregated signature. So it's actually very much, that's actually the thing that Ben Bonnet and other guys, the BLS guys, actually created in 2001. And the idea is that instead of one guy, you have many people. Let's say you have like all of us in the room, and let's say there is some statement that we need to sign collectively together. We sign a petition, you know, that we don't ever wear masks, you know, in this universe. So we, all of us like sign, and we have to have a proof that we actually signed the thing. So for this proof, you need to have many keys, right? Like each of us has to say no more masks, and then you know you sign. And then it becomes like a jigsaw puzzle. Please raise your hand. Ever any of you actually assembled a jigsaw puzzle? I never did this, but I've seen other people doing it. So so that's the idea of jigsaw puzzle. You know, we say okay, no more masks. You know, and then let's say some of you are objecting this and saying no, I'm going to leave, I'm not going to sign. But the rest of you are saying okay, I'm going to sign. And then each of you, when you sign, you have this file or mathematical object, which is like a piece of this jigsaw puzzle. And then you give it to me, and I actually connect the pieces, and I have the jigsaw puzzle, and this thing is called an aggregated signature. It actually is much stronger because it's common, it's opinion of many of us. So there are like signatures like 11 out of 10, 11 out of 20, like 100 out of 1,000. You have all kinds of things. It's basically people making collectively decision, and it's a proof of this decision. So that's something which is called a threshold signature, and it's actually also being used widely now in blockchain, because in blockchain you have many computers. So for instance in ETH2 you have to have a signature that something is true, and the way they do it in ETH2 is using an aggregated signature. Another super cool use for aggregated for threshold signature is something which is called common coin. Have you, please raise your hand if ever any of you heard about a common coin? Okay, it's a very interesting mathematical object. What it means is that let's say each of us has $1 now, and we like collect these dollars, we have $100, and we decide to do a lottery, and one of us gets like this $100. So 100 people collected $1 each, and then there's a lottery, and we need to randomly pick someone. If we just say, okay, this guy will pick the winner, he may actually pick himself, So there's a problem, the mathematical problem of a common random number generation. You need to generate the random number, but we cannot trust any single of you, surely. So we need to somehow to have the collective to generate the number. And it turns out that the same threshold signatures are actually the most effective way to solve this problem of a common coin, where we need to generate this common random number, and they're being used on things like blockchain lotteries, right? Literally, like how do you do a lottery on blockchain? Well, you can actually do it using this threshold signatures. But now I'm actually going to talk about a different thing called threshold encryption. And this thing is like works like totally magic on Scale chains. You can also implement it on other chain. And it allows you to totally and provably eliminate MEV and eliminate front running. So let's discuss how it works. So basically, okay, there's this slide. Okay, what front running is, right? We just discussed. It's very simple. Users submit transactions. Bad guys like miners and all other bad guys, you know. They see the transactions and they exploit it. And the simplest thing is, like, you guys know Uniswap, right? Please raise your hand if you understand how front running on Uniswap works. It's actually very similar in a sense to the example I was talking about, like a ticket to Rammstein. Basically, you send the transaction and someone else like buys, and then you have to buy in a more expensive way. It's not exactly like this, but the idea is pretty much the same. So when you actually use Uniswap, you're saying, okay, that's great, but then other people are watching it, and then actually they're running more transactions in front of you, buying the same token, and then your price actually ends up to be higher. So that's actually really bad. Now, so what usually happens in general in this front running on MEV, you submit a transaction is in the pending queue on the blockchain, doesn't execute immediately, and then people see it, learn, and like exploit it in this way or that way. And then you execute the transaction, but that time is actually ready to be exploited. So that's the process. It's a very simple process. And so the way threshold encryption works is that it's very much the same as threshold signatures, but it's a way to commonly encrypt and decrypt. Please raise your hand if you ever encrypted anything. Right? So usually have a secret key, you know, you put the key, then your document is encrypted, then you get to the conference, you forget the key, and like you screwed, you can't decrypt the document, right? That's usually how it works. So threshold encryption works a little bit differently. There's a key, it's a key. I see all of you guys. And all of you guys have keys, your private keys. And I can say, I will encrypt to this group. And then I take like something and I encrypt it and I give it to you guys. And none of you can decrypt it. But if a sufficient number of you can get together, maybe 2/3 of you, right? Usually, 2/3, super majority, you can decrypt. But again, it works like a jigsaw. Each of you decrypts, gets your jigsaw puzzle, which looks like totally chaotic and random. But when you put together your jigsaw puzzles, magically you actually have your document back, thanks to this guy, you know, in French jail, you know, like 70 years ago. That's really interesting mathematics. So that's threshold encryption. And so the way you protect against front running, like probably, it's actually very simple to explain. Let's go back to my previous slide. So what you do now, imagine like you want to buy a ticket for Rammstein, but you don't tell anyone, and you send an encrypted like letter to the guys that sell tickets, and they decrypt it, and only when they decrypt it, they know what you want to do. Maybe you want to buy ticket to Rammstein, maybe to Lady Gaga, maybe to Britney Spears. No one knows because it's encrypted, so people can't exploit it, and then when you send it to the guys that sell tickets, the tickets office, they decrypt it and sell you the ticket. But when they decrypt it, it's too late to exploit it because they already got the information. So basically that's the idea. You have Ethereum blockchain or Scale blockchain, something which is Ethereum compatible. It can actually be done as extension to Web3, JS, Web3 PY. User uses threshold encryption to encrypt the transaction. The transaction is encrypted to a large committee of nodes. In our case of Skale, for instance, there's a blockchain and the nodes run the blockchain. And so the user encrypts the transaction to these nodes, not only to one of them, but to the group of them. The transaction looks totally like random, like chaotic, you don't have any information from it. And then the transaction is actually committed to the blockchain, it goes into the block. In an encrypted way, inside the block, the transaction is encrypted, and only after the block is committed to the blockchain, the transaction is decrypted and executed. By that time, it's impossible to front run because the block is already there. It's impossible to put something out in front of the block. So that's really a magic way to execute, to fight front running. And it actually works magically. You don't need to modify anything, your solidity, whatever. You can take Uniswap and deploy it on Scale, and it won't actually have front running. And then another thing I wanted to mention is another really cool algorithm. This encryption requires some type of cryptographic keys, so you need to have some initial ceremony to create those keys. It's called DKG. We implemented in Scale. In our case, we implemented on Ethereum mainnet, and actually all of this code is open source. So if you guys want to use this threshold encryption, protect against front running, what you can do, we have all of our stuff on GitHub, Scale network, we have mostly C++ implementations of threshold signatures, and threshold encryption. Our signatures are compatible with Ethereum using the same mathematics as Ethereum precompiled contracts. And so they're compatible with ETH. And we also have Solidity implementation for DKG. So you can use all these things. And that's the end of my presentation. I hope it was useful. Let's ask, maybe talk some questions if there is some time.
How would you, I assume you would encrypt the whole transaction. So how is the metadata encrypted too?
That's
what
a good point.
Transaction spamming?
That's a really great point. There are some things you can encrypt. For instance, gas price. Because if the gas price is encrypted, you don't know if there's enough money to actually put this into the block. So you don't encrypt some things like gas price and some other things. What you actually need to really encrypt is when you have solidity. The arguments of the solidity you need to encrypt. If the arguments are encrypted, that's great. Maybe also encrypt the function itself, which is not so important. You know which function you execute, solidity. But for Uniswap, for instance, in the example of Uniswap, if you encrypt the arguments, the token, the name of the token, what you want to buy, what you want to sell is in the arguments. So it actually fully protects against front running, even if you just encrypt the arguments, but generally you also encrypt the name of the solidity function that you're executing. Any other questions?
What's the trade-off of it? Like, what's the trade-off of having this feature? Just like
it's almost no trade-offs. Actually, the concept of a committee exists already in all over proof of stake. So, for instance, if this is actually, I offer it to ETH2 guys if they want to implement it. I've actually offered it to Vitalik on a ETH research board to use this, because this could also be easily implemented in ETH2, because the committee is already there, right? So the committees need to have the threshold keys. So yeah, there are two things. There's the ceremony, the crypto ceremony, that to derive the threshold keys, because we do it on the ETH mainnet, it's pretty expensive. So in our case, it's maybe like, depending on the gas prices, I think like several $100 when the gas prices are low, because we do all the DKG on the mainnet, but could also be done outside of the mainnet. So you pay for DKG, and you also have to have the committee, the keys, but then it actually becomes easy. The actual encryption also requires lots of, you need to implement it. Currently we have C++ implementation. I believe some other guys have implementation in Rust, but it's not so widely implemented, threshold encryption.
You mentioned that it's quite expensive to do this signature verifications on mainnet. Is there any possibility of doing something where you're aggregating multiple?
Yeah, this actually could be used, that's a good idea. It could be used also, you could use like ZK, zero knowledge to actually aggregate signature verification, everything. So you could do it off-chain. We didn't do it because it's just lots of work, and all this ZK, snarks, starks, just so many of them. We are waiting. At the moment, these things are really like expensive, like engineering-wise. Maybe in the future there will be some framework. Ask people, is there like any like simple framework for ZK? and it doesn't seem to be at the moment something that you can just like plug in and say, I want to do this and this. In the future, once they have it, then I think we could do things like this that you mentioned, make it cheaper using like ZK proofs.
And one of the things that Ethereum mainnet will support like a precompile for BLS signatures. What, do you know like the status of that?
Yeah, so this is actually interesting thing. They already support a weird BLS signatures that we currently use because there's nothing else. Because they have a precompile on for ZK that can be used for ZK, there's also already a precompile. This ZK thing is using a very strange curve for the signatures called Alt BN 128. And it's not the best, it's slow, and it's not good for signatures, but we're using it for signatures because there's nothing else. We are waiting, they are planning to do a good curve, which is BLS 381. They are planning an implementation of it. I think it's been planned and it got from one fork to another, they've moved it. We actually are looking for it really at scale because that will actually make our life better, faster and better and cheaper. But so far, I don't think they included it in the London fork. Maybe they do it later.
You can change the BLS signatures though, right?
Yeah, so they changed two stuff, uses this BLS. I mean, what happened with BLS, there were all kinds of curves, and now people kind of converged on BLS 381 curve, which is really great because you can have, you need like for stuff, you need like JavaScript implementation because the browser needs to send it. So you need JavaScript, you need Python, you need like Rust, people just need all languages. And this BLS 381 was great is that because it's like standard, there are already so many implementations. But it's the beauty of ETH2, which is not really useful now, but ETH1 doesn't have it, so.
So just understand, you already, so you have like the side chains that you're running, and you have built that in this miner front running?
Into the sidechain, exactly. In the case, every node, so there's the blockchain. Every node has a. We do DKG at the beginning when we start the blockchain, when we bring it up. It does the DKG and derives all of those keys. And once the nodes have the keys, you can use threshold encryption. You can use threshold signatures using these keys. So the nodes, when I say that they collectively decrypt, the actual, in our case, just the actual nodes in the blockchain decrypt. It could be also a separate committee. It could be.
But is it built in like automatically?
Automatically for Scale, yes. You won't actually notice. You don't need to know anything.
So you just send a normal transaction.
Exactly. You will. It's totally transparent for the user. The only thing when you send the transaction, you need to once you have it, you need to encrypt it. So after it like goes out of Web3.js. It needs to be, you need to use our library to kind of tweak it so it actually the body of it gets encrypted.
You have a different provider inside that like encrypts it before it's
correct. Yeah, so it can be used with Web3.js, but you need also to use another JavaScript library.
How much extra gas does this cost? Because you're obviously adding it in some kind of pre-smart contract thing?
That's a great question. So in our case, our gas is very cheap because we have app chains or side chains. So, but it will use a little bit more gas because first of all, when you encrypt, the size of the transaction will become larger. But again, in our case, we don't really care because our gas is cheap. So
and also, does this change the TX origin?
it stays the same. So TX origin, it stays the same.
So you modified the EVM to...
No, the origin is encrypted, I believe the way you send to stays the same. Where you actually send the transactions, the smart contract.
Yeah, but the from is important. The message sender, right?
Sorry, the message sender is also not encrypted because of the gas. You need to check how much gas this account has. So message sender, message from to, gas price are not encrypted. Nouns not encrypted.
And what would be beneficial to the transaction spending? Because you could spam the miners with invalid transactions. If they're encrypted, you don't know beforehand if they're invalid.
Right. But they will be just out of gas, right? If they will at some point get out, they will still spend gas, right?
Yeah. What if
if they are totally. In our case, again, it's Archie, so we didn't do it yet, but we could penalize them a little bit for this in gas or somehow. In our case, gas is only used on Scale as a protection against denial of service because our chains are app specific, and in most cases, it's much less important. The guess things are much less important. But we could do it. Yeah. If we see lots of people doing sending corrupt transactions and encrypting them, we will introduce some countermeasure. We don't have the countermeasure yet, I believe, because we're like a startup. So you know, they're coding like throwing away everything which we can throw away. So we didn't get to this point yet. Guys, thank you so much. Okay, sorry.
Yeah. I was wondering, like, do you some nodes might come and go, and so what happens if you need to change some keys or rotate them?
We need to. Yeah, that's a great question because proof of stake itself requires 2 thirds. In our case, the signature is also required 2 thirds. Yeah. So it's pretty much on the blockchain. If on the proof of stake blockchain, if more than 2 like 1/3 of nodes are dead, not dead but they are out, it will stop. And then when you bring them back, this will run. So in our case, it's the same thing. So threshold encryption will stop, blockchain mining will stop if more than 1/3 of nodes go down.
What happens if there's a new node coming in, it needs a key to decrypt the message?
Then you need to do another DKG, right? That's but then you can the next one we can do our chain and not on the mainnet because like chicken and egg. Once you have our chain, things become cheaper for us, so the next one can be almost 0 price for us. While the first one don't have a chain, so we actually run the DKG on the mainnet. So, but you have a great question. The unfortunate, there's no, I mean, that's the only thing in mathematics which does kind of the work, and the DKG you need to repeat, at least we repeat it every time a new guy comes. There is actually some mathematical papers that allow you when someone comes not to regenerate all of the keys, but somehow incrementally do things. And we are planning to study this in the future. Currently, we just did the simplest implementation. New guy comes, so we just regenerate keys.
Thank you.
Fantastic, guys. Thank you so much for asking questions.
Awesome.